Okay, yeah. I think maybe Shannon is not coming today since Wesley just finished the exams early and is definitely not coming early today because she told me that she's going to be at the vet. Who else is not in yet? Xun Xun, Kai Hong, Lian, Min Gok, Min Shan, Shen, Shen, Brian, and Zhang Jie. Okay. Yeah, let's begin class away, guys. First and foremost, let's go through each and every one of these questions here and please check your answers, guys. The first question here is that a stationary smoke particle is hit by a fast-moving nitrogen molecule. Which role describes the motion of the smoke particle and of the nitrogen molecule after the collision here? The answer is going to be A. A smoke particle moves and the nitrogen molecule rebounds. Now, you often see this in your IGCSE question and quite frankly speaking, right, these kind of questions are quite gray one because if you were to think about it, right, how come the stationary smoke particle here, when it was hit by a nitrogen particle, it only moved, it definitely moved this one here. So C and donkey definitely is out of the question here. But then there is a possibility for the nitrogen molecules to stop as well if all the momentum is totally transferred to the smoke particle here. But then because the fact that in this particular question here, they say that, it was a fast moving nitrogen molecule. So the likelihood of it stopping would be quite negligible. That's why the answer here is going to be move and rebound. So you'll see these kind of questions quite often in your IGCSEs and you have to be very careful with these type of questions here. Now, second question here, they say at room temperature, iron is difficult to compress. At the same temperature, oxygen is much easier to compress. Which comparison of the structure of iron and oxygen explain this? This kind of questions here, guys, it's very straightforward and it's going to be a standardized question. Like I mentioned last week here, the reason why we can compress oxygen because it is a gas molecule here, right? Gas molecules, there are generally a lot of space in between each and every molecule, meaning to say when we compress it, it can easily be compressed. Whereas for this, they say this iron here, iron is generally a solid particle, right? Solid particles, basically they are already in lattice arrangement and they are already touching each other. It is much harder simply because there is no space in between them. So look at the logical answer, only iron particles are closer together. Give me a minute, guys. Okay, so A it can be none other than A for this part here. Then after that, the third question here, water in the beaker evaporates when it is left on a bench for a period of time, increasing the surface area and increasing the temperature of the water. Each change the rate of evaporation. Which role is correct? Which in this case here is supposed to be D. The rate of evaporation increases. Why? Because like I mentioned last week, there are mainly three main factors that affect the rate of evaporation, which is going to be surface area, the temperature, and also the humidity. For those who forgot what humidity is, to be humid is to be wet. For example, Malaysia is considered a humid country because it's generally quite wet in the environment, right? So these three are the main factors that affect the rate of evaporation. Increasing the surface area, meaning to say you are exposing more. Okay, oh my God. It's supposed to be the rate of evaporation. What the hell? Siri just activated. Okay, but anyways, well, that scared me a little bit. But anyways, yeah, from here, increasing the surface area, basically you are exposing more water particles to the surface, right? So sorry, to the surrounding. And thus rate of evaporation is definitely going to increase. When you increase the temperature, what's going to happen is you are essentially injecting energy into these water molecules. And like I mentioned last week as well, whenever these surface molecules gain enough energy, they will break the bonds in between them and escape to the surrounding as gas particles. So obviously the rate of evaporation increases as well. Okay. Yeah, shouldn't be a question for this part here. Then which statement about the evaporation of liquid is correct? The answer given is going to be the most energetic molecules escape from the surrounding and the temperature of the liquid decreases. Now, this is definitely true. Why? Like I mentioned last week, right? If evaporation were to occur, generally the molecules at the bottom will supply molecules at the top with energy, and thus they will eventually evaporate to the surrounding. All right. When this happens, energy in the overall liquid is decreased, right? And this will obviously cause the temperature to decrease as well. Okay. So nothing much for that. Then it says that liquid turns into a gas. This occurs only at a particular temperature and the change happens throughout the liquid. Obviously, it is going to be boiling. I've mentioned this last week. The main difference between boiling and evaporation is that boiling only occurs at boiling point, which is for water 100 degrees Celsius. Whereas evaporation can occur at any temperature. It doesn't matter if it's 0 or 100. There will be evaporation occurring. And then the second thing about evaporation is that it only occurs on the surface, right? Whereas boiling happens throughout the whole liquid. It's going to happen throughout the whole liquid. If you've ever boiled water for Maggi mee before, you will definitely understand what I'm talking about. For those who are too privileged to boil their own Maggi mee, go boil it tonight. Then looking at this next question here, which role describes the arrangement and the motion of the molecules of gas? In gas, arrangement is obviously going to be far apart and motion is obviously free to move about. Vibrate is only for solid particles, so the answer can be no other than A here. Then after that, what does this question want? A bubble of air of volume 3 mm3 is underwater. The bubble is a depth where the pressure of the air inside the bubble is 4 times the atmospheric pressure. Okay, it's 4 times the atmospheric pressure, basically 4P, right? The temperature of the air in the bubble stays the same and it rises to the surface. What is the volume of the air in the bubble as it reaches the surface? If it reaches the surface, and just now it already said that in the water, it was 4 times the atmospheric pressure. When it reaches the surface, it will just be only atmospheric pressure, right? From here, you can just start to use your Boyle's law formula. P1V1 is equals to P2V2, which is going to be which is going to be 4P multiplied by 3 divide, which is equals to P2, which is just P, and then you're looking for V2, right? So essentially here is going to be 12P divided by P, which will eventually give you 12 mm, guys. This is how you're supposed to construct the formula for these kind of questions. Of course, you have to understand that if they say there is 4 times the atmospheric pressure in the water, when it reaches the surface, only atmospheric pressure is acting on it, right? And thus it will only be P. So the key point here is to identify that here is 4P and here is P. Very important. Okay, then after that, the next part here, it says which role compares the separation and the motion of the molecules of a hot gas with those of a cooled liquid. Obviously, the separation is much greater in a hot gas and the motion moves much faster, simply because they have more energy and they're trying to break apart from each other, right? So it can be no other than A for this question here. And the final question for the ABC part. The fixed mass has a volume of 25 cm cubed and a pressure of 100 kPa. Guys, I must emphasize this word. A lot of times you guys will always just see I know this is a general trend for students, by the way. They'll always just see this number here, right? And then they forget about everything else. They just assume that it's going to be pascals. But in reality, if you look closely, there's actually kPa here. kPa means to say 100,000 pascals. When you press it into a calculator, it will be 100,000 pascals. So be careful with this. Make sure you know these prefixes. Then after that, it says that the volume is slowly decreased by 15 cm cubed at a constant. Decreased by 15 cm cubed. at a constant temperature, meaning to say the volume 2 is going to be only 10, right? If the volume 2 is only 10 using the P1V1 equals to P2V2 formula again, it's going to be 25 times 100 divided by 10, which is going to be, oh, what? 25 times 100 divided by 10. You get 250,000 pascals. The answer is supposed to be donkey here. Let me double check this. The volume of the gas is slowly decreased by 15 cm cube. Yeah, so it's going to be only 10 cm cube. So it's going to be 25 times 100,000 divided by 10. Yeah, the answer is going to be donkey, not B here. 25 times 100 divided by 10. Yeah, it's going to be donkey for this part here. All right. Yeah, before I move on to the next part, anyone with any questions for the ABC part? Anyone got a different answer from me that you would like to clarify? Okay, good. 100% absorption rate. No questions. If there's no questions, then moving on to this next part here. Yeah, generally it's quite straightforward as well. Let's look at the questions together. What do we have? In figure 7.1, the small circle represents molecules. The arrows refer to the change of state from the arrangement of molecules on the left to the arrangement of molecules on the right. Obviously, it's solid, it's liquid, and this obviously gas. Complete the following, blah, 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 blah. Change state X is from solid to liquid, obviously, and Y is obviously liquid to gas. Whoever that lose this mark, good luck, have fun. Explain in terms of the forces between their molecules why gas expands more than solid when they undergo the same rise in temperature. Now, this has to do with the fact that because they have strong forces of attraction between each and every one of them. For example, if today you try to heat up what's it called, a metal rod, let's say for example a metal rod, if we were to look at it in terms of the molecular structure, metal rods are the reason why they are so solid is because the molecules are touching each other, and the reason why the molecules are touching each other is because they have strong forces of attraction pulling each and every one of the molecules together. Today, if you raise the temperature, right, what you're essentially doing is you're trying to supply energy to this metal rod, right? And when you try to supply energy to this metal rod, what's going to happen is initially these molecules are going to gain energy and they're going to vibrate more vigorously. And when they vibrate more vigorously, obviously they are going to start to expand. In fact, actually, this question here is a little bit on what we're going to learn today, guys. But let me just give you a quick run through on this one first. Basically, when they supply energy here, these molecules are going to vibrate, and once they vibrate, they will actually vibrate in a larger position here, a larger volume here, and ultimately they will expand, right? But of course, the expansion is going to be very, very small compared to gases, simply because the forces of attraction between each and every one of these molecules here are it's much higher than gas molecules are, and thus they generally will not expand as much as gases. So if you look at this answer here, you'll see something like molecules have strong forces of attraction between them, gas molecules have no forces of attraction between them, or you could either write easily increase separation. Yeah, no, not this one. Just write this one better. So if I were to structure an answer here, it would be something like solid molecules super strong forces of attraction between each other. Large amounts of energy is needed to separate the molecules, whereby gas molecules have almost zero, weak or zero forces of weak let's just say weak it's actually not zero, weak forces of attraction between each other. Less energy is needed to pull Then after that, what do they want from you? A cylinder of volume 0.12 meter cube contains a compressed gas at blah blah blah. A valve is open and all the compressed gas escapes to the cylinder into the atmosphere. The temperature of the gas does not change. Calculate the volume that the escape gas occupies at the atmospheric pressure of blah 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 blah. Obviously, this one here is going to be using your Boyle's law formula yet again. P1 V1 equals to P2 V2. Or it's just a matter of identifying your information. Obviously, this is V1. This is going to be P1. And obviously, this is going to be V2. So P1 V1 over P2 is going to be equals to V2 here. Press everything into the calculator, and you're going to get somewhere around 0.216 meters cubed, basically. Yeah, I think all of you guys shouldn't have a problem with this kind of questions here. It's like, it's 3 marks, guys. So it's just a simple formula and identifying everything, put it in, solve your algebra, you will be able to get an answer of 0.216 meters cubed. Yeah, but for those who did not bother attempting it, then it's going to be a little bit hard. Okay, yeah. Any questions from this part here before I move on to the next question? Anyone don't understand what I'm talking about or have any questions they would like to clarify? Good. 0 questions again. Moving on. Yeah, so many questions again. Yeah. Looking at this second question here, liquid and gases are 2 states of matter. In both boiling and evaporation, the liquid changes into gas. State 2 ways which boiling differs from evaporation, like I mentioned just now, is either going to be the surface area. Sorry, boiling occurs throughout the liquid. Evaporation occurs only on the surface. Boiling occurs only at boiling point. Evaporation occurs at any given temperature. So these answers here is going to be quite straightforward. You can see, yeah, these are the answers given as well. You can even write bubbles are formed when boiling occurs. But generally, I would not write this. I would just definitely write that surface throughout any temperature, boiling point only. These are the 2 most standard answers for IGCSEs if they ever ask about boiling and evaporation, which is quite honestly common sense. I don't think anyone needs to memorize that. If you've ever seen anything boil or evaporate before, you understand what I'm talking about. Before injecting a patient, a doctor wipes a small amount of volatile liquid on the patient's skin. Explain in terms of molecules how this procedure cools the patient's skin here. Now, if you've ever experienced a jab in the hospital before, usually they will wipe your skin with alcoholic swabs or whatever numbing cream they might have. Then only they'll inject you. Now, the reason why they do that is to, of course, kill any infections or any bacteria that may lie on your body. And then next, of course, is to ease the injection so that it doesn't hurt as much. But actually, I would say if not for the phobia of needles, I think having an injection shouldn't be a problem as well. In fact, I just come to realize that Gilbert actually has needle phobia, in the sense he can't look at the needle. It doesn't hurt at all, right? But just that when he looks at something poking into his skin, his brain just go into defense mode and then he just shut down automatically. It was quite funny when we saw that happen. But generally, yeah, I think that's a form of phobia which can't be controlled. But if you guys ever been jabbed by a nurse before, I'm pretty sure you know what I'm talking about. It's actually equivalent to an ant bite. It absolutely does not hurt. But anyways, going back into this question here, explain in terms of molecule how this procedure cools the skin. I've mentioned this in class last week as well. Let me just repeat this again. Today, if let's say this is the layer of your skin, right? And when they put some form of volatile liquid here, right, what's essentially happening is that the energy from your skin is being absorbed by the water molecules here. And when these water molecules absorb your skin's energy, what's going to happen is they are actually going to go through evaporation and leave you with a cooling sensation here. this concept is the same for sweating as well, guys. So generally, you see these kind of questions asked a lot in your IGCSEs, and you must be very, very well versed with these type of questions here. So if you look back at these answers here, right, look what they want from you. They say that the more energetic molecules escape from the liquid, average speed decreases, temperature of the liquid decreases, and this last part is just like for the sake of writing only. Thermal energy is conducted away from the skin or so on, right? If you ask my honest opinion, I don't think this question deserves 4 marks. All these things is like just repeating each other. It's like saying that, okay, I'm a boy, so I'm not a girl. Then I haven't give birth to a child yet, so I'm just a son, not a father. So if you ever see these kind of questions in your IGCSEs, right, that you feel that it has like super long marks and not much what's called verification of the information, you can just start writing some nonsense, like I'm a boy, so I'm not a girl, those kind of answers, which you will see in these kind of answers here, right? So if I were to write down a more specific answer, it will be something like as the volatile liquid comes in contact with skin, energy from the patient's skin is being absorbed through evaporation. Energy from patient's skin is being absorbed by the liquid and goes through evaporation. Since the energetic molecules escape, evaporate and escape, evaporate and escape to the surrounding, the less energetic molecules are left behind, giving a cool sensation. Okay. Then after that, I don't want to explain this answer again. It's basically the same thing repeating over and over again. Gas can be compressed, but liquids are incompressible. Explain in terms of molecules why liquids are incompressible. It's because liquids are already touching each other. The molecules are already touching each other. The liquid molecules, they are just super disorganized. It's not that they are not touching each other. They're just super disorganized already, and thus, if they're already touching each other, if they are already touching each other, it means to say there is no space in between them, and thus it is harder to compress. In the math scheme here, they also give large repulsive forces when moved together. This is a bit weird. Don't bother writing this down. It's irrelevant. Just say that the molecules are already touching each other, and there's no space for them to be compressed. Let me write this down in case you guys don't know what I'm talking about. All liquid molecules are already touching each other. And after this statement, explain in terms of molecules, any change in the pressure of the gas when the volume reduces at a constant temperature. Obviously, what's going to happen is when the volume decreases is reduced, obviously the pressure is going to increase. Now, why will it increase? I mentioned this last week as well. Let's imagine today this is a square-shaped balloon, if there's such a thing. And let's just say inside this square-shaped balloon, there are air molecules. And to be more specific, there are only 9 particular air molecules in here. Of course, what I'm saying is just for explanation of there is definitely going to be more than 9 molecules inside any given object here. But for this case of understanding, we're just assuming there is 9 molecules here, right? as the volume decreases, what's going to happen is, right, the same amount of air molecules will occupy a smaller amount of the space here. Remember, I mentioned this last week, and the reason why there is pressure inside any container or any balloon or anything for that matter is simply because these air molecules here constantly collide against the walls of the container. They constantly collide against the walls of the container and thus creating a force per unit area. If you remember about the pressure formula, I've mentioned pressure is equal to force over area, right? Today, if I have continuously increased collision against the walls of the container, what's going to happen is ultimately force per unit area increases and ultimately the pressure increases. Now, in terms of volume, why is it that when we decrease the volume, the pressure is going to increase even more? It's simply because in a smaller space, the air molecules here, they collide against the walls more frequently because there is going to be less and less space for them to move around. And because of this, we can definitely say that for the same exact area, the force per unit area is increased and ultimately increasing the pressure here. Now you'll see these type of questions very, 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 very often in your IGCSEs, and most of the time it will contain a lot of marks on them. The key word here, guys, are always with collision. The keywords are, pay attention to this, is always the air molecules collide against the wall. It must collide against the wall to have an increased force per unit area, and the molecules hit the walls more often when the volume is less. This causes a greater force, which is directly proportional to the pressure of the container, guys. These are the few keywords that you must write down when doing these kind of questions here. It's always collision against the wall, hit the wall more frequently, creating a greater force per unit area against the wall. Very, very standard question with a very, very standard answer. So from here, once you understand that, obviously the pressure increases. Why? Explanation, all right. Explanation is as the volume decreases, the same amount of molecules occupy a smaller space. This causes the rate of collision of air molecules against the walls of the container to increase, ultimately increasing the force per unit area of the wall. Okay. Anyone don't know what I'm talking about for this one here? This is very, very important. If you don't understand, you better ask now. Good. Everyone understands again. Let's see how you guys do later on in the questions. Yeah, moving on, next part here. Obviously, expands the most is gas, expand the least is going to be solid, no explanation there. A liquid is heated so that the bubble of its vapor rises to the surface and the molecule escapes to the state. The name of this process, obviously, is boiling. Right? Heated so that bubbles of its vapor rises. Yeah, this is going to be boiling. At a lower temperature, molecules escape to the state. This is evaporation. Evaporation is standard here. Then after that, what's this? Describe how the molecular structure of the liquid metal differs. I'm not going to explain this. This is going to be like repeated over and over again. You can, yeah, this is going to be repeated over and over again. You can write it down for yourself. Just explain how the solid molecules differ from the liquid molecules. Yeah. Then after that, what's this final question? P1 V1 equals to P2 V2. A piston is pushed into the cylinder. The volume decreases from 820 to 330 here. The pressure gauge measures the blah, blah, blah. After compression, After the compression is going to be blah, blah, blah. The temperature remains constant. Calculate the value of pressure before the gas was compressed. This is V1, this is V2, and this is going to be your P2. You are actually looking for your P1. So P1 equals to P2, V2 divided by V1 here. Press everything into the calculator and you will get 330 times 20,000 divided by 820. You'll get super random number, which is 8049. And like I've mentioned many times in class before, if you're given these kind of answers, when you write it down on the dotted line here, you can only write a maximum of 3 significant figures. Okay, so it's going to be 8050 PA. Or alternatively, you see in the mark scheme, they always give in 2 significant figures. So it's going to be 8,000 here. Okay, everybody. Yeah, this is going to be the same thing again. Solids have a fixed shape. Liquids adapt to the shape of their container. Gas are filled with containers. In terms of forces between molecules, why solid and gas have these properties? Solids obviously lattice arrangement, strong forces of attraction between each other. Liquids are basically not fixed. Their arrangement they can easily slip across each other, and they have relatively weaker forces of attraction. Somewhere around here. Weaker forces of attraction. Then after that, gas molecules, they are very far apart, simply because they have almost no forces of attraction between molecules here. A standard question with a standard answer. Just look at this here itself, we repeated 1,000 times. You already know it's going to be easy as long as you know how to write it down. And thus the importance of homework. Usually year 10, everyone, they are on the no care state until your year 11. Then I'll watch you guys panic. No. Okay, anyways, having said that, any questions from this paper here that you guys don't understand before we move on to the next chapter here? Anyone don't know what I've been talking about for the past 30 minutes or have any questions they would like to clarify? Ask now. Good. Absolute no questions. Then we'll move on to the next chapter here. Okay. Yeah. Let me just give you a run through of what we're going to be learning today. Okay. Okay. Now we're going to learn a few important things today. Number one, first and foremost, we're going to learn why hot expands and cold contracts in terms of the molecules. We're going to identify the applications of why some of the time, no, not some of the time, most of the time you'll see that the high tension cables are always in a slanted manner. Why are there gaps in between the railway tracks, and why are there gaps in between the wings of an aeroplane that's flying at a super high speed? Then after that, we're also going to understand why liquid and gases, how come their expansion is going to be more or less, and then depending on the expansion, whether it's more or less, how are they going to affect the arrangement or the reading of a thermometer here. We are also going to learn a very specific term known as fixed points in your IGCSEs. If you ever see this word fixed points, it is basically going to be 0 degrees Celsius and 100 degrees Celsius, regardless of whatever information they give you. More detail on this later on. We're also going to learn the usages of a thermometer. Basically, thermometers measure temperature through the expansion of liquid, and that liquid is going to be 2 specific liquids, namely being mercury and alcohol, not any other liquids. I'll explain more in detail later on. Then after that, this is the part where students will generally suffer a lot. They do not understand the difference between sensitivity, linearity, responsiveness, and range. And yeah, I've taken the time to even tabulate how to improve what. This will always be asked in your IGCSEs. By the way, this page here, I dare say, is going to be one of the most important pages of this exercise here, and this is basically a table to summarize everything that I mentioned on top. Okay. Then finally, we are going to learn that besides a thermometer, there is another thing known as a thermocouple that can be used to measure temperatures. And the reason why we use such a complicated device is simply because it can measure super high temperatures, meaning it could be anywhere from negative 200 degrees Celsius to 1100 degrees Celsius here. And it has super rapid response, namely because it is using the expansion of metals, which have a much smaller specific capacity. In other words, it's easier to heat up metals compared to heating up liquids simply because of the specific capacity. For those who have gone through this in school, you generally understand what I want to talk about, and please take note on all the things that you don't know what your school teacher has been talking to you about. Make sure you ask the questions, guys. But yet again, sometimes I just feel that I'm talking to myself. But anyways, the task must go on. Let's look at the first part here, guys. Thermal expansion. If you ever experienced thermal expansion before, you definitely understand that heat expands and cold contracts. Personally, my first experience of having seen thermal expansion is when I was in primary school. I don't know if you guys ever seen this before. In primary school, right, they have this very dumb experiment now, right, where it has a metal hoop here. Right, this metal hoop will exactly fit through one specific metal ball here. You can say the diameter of this metal hoop is the same diameter as this metal ball here. Before you heat it up, what happens is the teacher will always take this ball and it will just like pass it down into this hoop where the ball starts falling down through the hoop, right? Then after a while of doing this, when she wanted to introduce thermal expansion, she actually took this metal ball and she started heating it up, and as soon as she started heating it up, right, when she put this metal ball into this metal hoop, what I saw was that the metal ball was resting onto this metal hoop already. It could no longer go through the metal hoop simply because it has gone through thermal expansion. And thus we understand that heat always expands, cold always contracts. Now, if we want to talk about it in terms of a molecular level here, like I mentioned just now, guys, in terms of molecular level, solid particles, right, generally they'll look something like this, right? And in terms of the movement of solid particles, they actually vibrate in a specific fixed position, meaning to say, when they vibrate, they could vibrate up to these types of volumes here. Generally, of course, this is going to be like the microscopic version of it. You can't say that, this solid particle is like vibrating such a large distance here. It's almost like a mini earthquake already, right? So this is obviously going to be a microscopic version of it. And generally, solid particles, they will vibrate at a fixed position here. When today we start applying heat energy to it, we are basically supplying the solid molecules with energy, right? And when we supply the solid molecules with energy, obviously its kinetic energy is going to increase. And once the kinetic energy increases, what's going to happen is they will start to vibrate in a larger space, right? Because they have more energy, right? So they'll vibrate in a larger space, and thus thermal expansion is born, my guys, from here to here, from here to here, from here to here, and here to here. And this is the molecular structure, representation of how heat expands and cold contracts are. The inverse is true for this one as well. Today, if let's say I were to chill it out, right, if I were to chill this whole thing out, what's going to happen is essentially I'm removing energy from these molecules here, and when they remove energy, they'll have less kinetic energy, and when there's less kinetic energy, obviously they will vibrate in a smaller position here, right, and thus ultimately we can say that the cold contracts them, guys. Okay, anyone don't know what I'm talking about for this part here? Good. So if you look at these statements here, right, it basically is a structured version of what I've mentioned just now, right? Number one, when heated, solid and liquid and gases gain thermal energy, the particles start to move about, their vibration take up more space, so there is expansion in all directions. When it's cold, when it's hot, it looks something like this graphically. The opposite is true. When the temperature falls, the material will get smaller, contracting. Liquid expands more when heated than solid because of their weaker bonds. Generally, gases have the least amount of forces of attraction, and thus they will expand the furthest when they are heated. Okay. Yeah. Can you guys copy this down first? For those who have my notebooks already. Hey, by the way, Shanice and Qingsheng, you guys received the notebook already, right? Oh, okay, great. Yeah. Um, yeah, copy this down first, then after I'll talk about the applications of what you're going to use heat expand and cold contract. All right, I think you all should be done copying all the keywords by now. Let's look at how the application of heat expand and cold contract works. Today, if you look outside your window, right, most likely you're going to see those high tension cables that supply electricity to your household, right? When I was younger, I always asked myself, how come, right, if I have all those high tension cables and all the poles here, right, you'll always see the cables are always in a slanted manner like this here, right? They are always in a slanted manner. They'll connect to each other, basically, right? But there's always going to be slanted in the scenario here. Now, if you think about why they slanted, actually it quite doesn't make sense on why, because in terms of engineering, we'll always try to maximize the efficiency of everything. Now, having a slanted line versus a straight line here, the main problem is that obviously you're going to use more material, in the sense that if it was one straight line, maybe it was only like 10 meters long. Whereas if you slant it a little bit more, right, maybe it will go anywhere up to like 13 meters long. In terms of engineering, I always thought about it and I think that actually it quite doesn't make sense. How come if you want to be more cost efficient now, right? It should all just have a straight line, then you have minimal amount of cost for the wiring now, right? Because you're using a shorter wire. But in reality, of course, you can never use it as one straight line here. Why? Because in a normal day, right, everything will be fine. For example, when the sun is shining bright onto you like your future, what's going to happen is this sun is actually going to provide heat to these wires here, right? And when they provide wires here, obviously, like we mentioned just now, heat expands, and what's going to happen is on a sunny day, these wires will slant even more because it has the heat from the sun has caused the wires to expand even more. But today, what if it is a not so sunny day? What if it's a emotional day where there's no sun and then there's going to be clouds and dark clouds over the sky? So what's going to happen is obviously when there's dark clouds over the sky, the temperature is going to drop. When the temperature drops, what's going to happen is cold is going to contract now, right? So these wires here, instead of slanting, they'll start to contract and they're going to straighten up themselves. The colder it gets, the more it contracts. So much that once it contracts too much, right, it will actually pull itself apart, and this will present a super large problem, because if the contraction is too much, we will say that there is too much tension on the wire, and ultimately the wire could face it could break apart, basically, right? It could snap apart, right? So from here, obviously, if you look at this in Malaysia, obviously this is not going to be the case, right? Because even no matter how cold it can get, like the coldest a night can get with a rainy day is probably going to be like 19 degrees Celsius, which is nothing much to brag about, right? But in other colder countries, like for example, winter countries like America, California, like Beijing, even, these kind of countries, right? They experience extreme cold weathers, and when they experience extreme cold weathers, right? The tension on these strings could be so much that it could potentially break itself apart, simply because the molecules are constantly contracting against each other. So obviously, if you think about it in a more logical point of view, we must have all these high tension cables in a suspended manner, simply because we are taking into consideration the hot and cold days. Okay, so it will be the same for the railway tracks as well. Today, if you've ever seen a railway track, right, you'll notice that there's always going to be like small little gaps in between each and every one of the railing, simply because when a train passes by all these kind of railway tracks, right, obviously it's going to create friction across the rails, right? And when there is friction, obviously there's going to be expansion, and engineers will calculate the amount of expansion needed here, and they will take into calculation the amount of gap needed for the expansion so that it does not buckle. Today, if you ever see a train derail or start to derail into a super bad accident, like for example, I think the recent one was the Malaysia derailing incident. Oh no, sorry, the Malaysia one was not a derailing incident. It was just a head-on collision between the two trains. Now, if you talk about derailing, the most common one we know is the Japan derailing of the tracks, all right. Now, why the reason why there is derailing of the tracks is because on a super hot day, right, the engineers did not take into consideration the expansion of the railway tracks. When these railway tracks expand to like the maximum here already, right, what's going to happen is because they have no more space to go, right? So what's going to happen is eventually the railway tracks will expand upwards like this. And when they expand upwards like this, eventually the tracks will look something like this here, right? And obviously when the train starts coming here, it's going to go into a super roller coaster ride. Derail, maybe flip a little bit, and then maybe some casualties. Maybe people are going to die, but definitely a lot of people are going to be injured. And this can actually be prevented if we have calculated the right amount of expansion here. Of course, in your syllabus, you are not expected to calculate any form of expansion here. That will be in your university days here. But the common understanding is that the reason why there is gap here is simply because of the expansion of the railway tracks. It's the same for these high speed, especially the air jets as well. If you've ever sat at a window seat before, you'll notice that on these planes, right, they will usually not be like one whole line here on, right? The planes are actually separated into three segments on. Why they're separated into three segments is yet again to accommodate for the expansion of the metal wings there, and thus not cause a super MH360 or what is it called again? I can't remember the accident that the plane was lost. But anyways, you get the idea, right? Basically, the expansion, it allows for the expansion of the metal wings here. Okay. No questions from this part here as well. Very good. Yeah, if you guys want to play around with the expansion of cold and hot, right? Actually, what I recommend you guys to do, right? You can do this at home, right? Basically, what you do is, right, if you want to see how the cold contract actually pull apart the tension of the cable, what you can do is you can take a cup of water, right? No, not a cup of water, a mug, basically, right? You take a boiler here, and then you pour 100 degrees of boiling water onto this mug. Continuously pour the water, even though it's overflowing already, right? You continuously pour it all the way until you finish everything from your boiler here. Then once you're done with this, right? Obviously, the concept here is that the hot water is going to cause the mug, which is solid molecules, to expand. Immediately after you've done pouring the hot water, right, what you can actually do is, right, you can take a super cold cup of water here, preferably like ice all the way, right? And then you take this super cold water and you pour it directly onto this mug here. What's going to happen is, right, you realize that your mug will eventually crack, if you did it the right way. Why? Because when the hot expands and the cold contracts, what's going to happen is some molecules are still in contraction. Some molecules are already in the expansion already, and because of these here, it will cause the molecules to pull apart, and eventually the glass cup will break into two or maybe break into 1,000 pieces. So be careful when you're doing this experiment though. When the center reopens, I'll definitely try to have this done in the center with proper supervision, of course. So that'll be something fun to look at in terms of the hot expand and cold contracts. So yeah, this is the reason why it will crack, right? Because some molecules are still contracting, whereas some molecules are already expanding. And that leaves a tension in between them and eventually cracking the cup. Okay. Yeah, looking at the time, probably we won't be able to finish everything. Let me just try to explain everything from here first. Yeah, probably won't be able to finish everything. Yeah, let's look at this part here. If you look at this next part here, it says that explain in terms of motion and arrangement of molecules, the relative order of the magnitude of expansion of solid, liquid, and gas. Basically, you are supposed to know how solid, liquid, and gas expands with reference to each one another. Okay, if you take a look at this example here, when a thermometer is placed in hot water, you will notice that the indicator first drops before it goes up. Why? If I were to redraw this statement here, today, let's imagine this is the cup of hot water, right? Let's imagine it's 100 degrees Celsius. Okay, today, if I were to put a thermometer here, which initially, let's say at room temperature, maybe it's like 24 degrees Celsius, right? When I place this thermometer in this hot water here, what's going to happen is, right, you most often realize that the thermometer, the reading will drop a little bit first. Maybe it will drop to 22 degrees Celsius. Maybe it will drop to the 22 degrees Celsius line before shooting all the way up to the 100 degrees Celsius line. And there is a specific reason to this. Can anyone guess why the liquid drops first before it rises? Anyone want to take a wild guess why? Good. Absolute no response. Just what I like. An absolute silent class. The surface is cooler than the volume of the water. Shani, it's a good attempt. Good attempt. But that's not exactly what I'm looking for. Let me tell you why, okay, guys. The reason why the liquid drops before it rises is because imagine this today when we place a thermometer into the hot water, right? Which part of the thermometer comes in contact with the water first? If I place this thermometer directly into the liquid, right, what's going to happen is the direct contact of the thermometer before it even reaches the liquid level inside is that the heat is going to come in direct contact with the glass first, right? And because it comes in direct contact with the glass, what's going to happen is this glass beaker here will actually expand first. The heat actually has to penetrate through this glass layer here before reaching the mercury or alcohol liquid here, then only can the heat expand the liquid and cause it to rise upwards. So if you think about it really logically, right, first and foremost, the liquid drops simply because the heat comes in contact with the glass first, right? And when it comes in contact with the glass actually expands. When the glass expands, the volume inside here suddenly increases and cause the liquid to drop a little bit. But once the heat penetrates through the glass layer to the liquid layer, which is going to be here, because liquid expands more than solid, right? And naturally, of course, the expansion of liquid is going to be much more than the expansion of the glass here, right? And this is the reason why liquid levels drop initially before it raises to the top. So if you look at these statements here, here's yet again the word structure of what I've mentioned just now. Initially, the indicator drops because the round conical flask expands when heated. Basically, the glass part here expands, right? Later, the heat reaches the red ink, causing it to expand. The indicator continues to rise as the expansion of liquid is higher than the solid. Okay, so this is the reason why, guys. You get what I'm talking about? Anyone don't know what I'm talking about, guys? Anyone needs an explanation for this part here? If you have no questions, please copy everything down, which I assume everyone already started copying down as soon as I was explaining. Okay, everybody. Next, we're going to talk about a thermometer. Yeah. Yeah, before we even go into the thermometers, right? Have you ever realized that thermometers are they're only going to be two specific colors in terms of the liquid? For the most common seen thermometers in school are the mercury thermometers, meaning to say you'll see that the liquid inside here is going to be like silver in color. And then the second most common thermometers that you will see generally in the doctor's clinic, which is going to be the red color thermometers, where the liquid inside here is going to be red color. Do you guys know the difference? Why is there a difference between the silver and the red one? No. Now, the reason why there is a difference between the silver and the red is simply because there are two different liquids here. This one here is generally mercury, whereas this one here that is red in color is generally alcohol. Okay. Now, why is it that we only use these two specific liquids? Why can't I make it orange in color? Why can't I make it blue in color? Why don't I use apple juice inside here? Why do I only specifically use mercury and alcohol? And the reason why we specifically use mercury and alcohol is because only alcohol and mercury are considered liquids with linear expansion. Now, what do I mean by linear expansion? Today, if you were to place mercury inside here, we already have the calculation, we already have the calibration for mercury already. It's going to be like, okay, let's say for example, here is 1 degree Celsius. After another degree Celsius here, 2 degrees Celsius here is going to be exactly, let's say for example, 1 cm. From here, we know that every 1 degree Celsius change in the thermometer is equivalent to 1 cm expansion of the liquid. It's the same for alcohol as well. Maybe alcohol will have a different expansion. Maybe every 1 degree Celsius change is going to be like 0.5 cm expansion of the liquid. And because they are linear expanding liquids, we can assume that the readings, the scaling here is going to be linear as well, in the sense that this is going to be like 1 cm, this is going to be another 1 cm, another 1 cm, another 1 cm, 1, 1, 1, 1, 1, 1, all the way until from 0 to 100 degrees Celsius. It's the same for alcohol as well. It will have a linear scale, which is going to have equal distance between each and every one of the reading. Now, today, if you were trying to be funny and then you try to put orange juice into a thermometer, right? Let's say you have orange juice inside a thermometer. Orange juice is considered to be a non-linear expanding liquid, meaning to say, right, maybe the first degree Celsius, it will expand by 1 cm. The second degree Celsius change in temperature maybe is like 3 cm. And then the third degree Celsius change is maybe like, in an extreme case, maybe like 5 cm. So your reading will always be like let's say, for example, here is 1 degree Celsius. Here will be 2 degrees Celsius, and then here will be 3 degrees Celsius here. You can see that the difference in length between each and every one of the readings, right, is going to be non-linear. And that is the specific reason why we will only use alcohol and mercury. Is because alcohol and mercury are the linear expanding liquids. And linear expanding liquids, it means to say they have linear expansion throughout each and every one of the temperatures here. So, having said that, right, if you look at here, it says that a thermometer has a glass tube sealed at both ends and is partially filled with liquids like mercury and alcohol. It cannot be any other liquid, or it cannot be orange juice, it cannot be apple juice, it cannot be your saliva, it cannot be the piss that you piss out. No, none of it. It must only be specifically mercury and alcohol, simply because these two liquids are considered to be linear expanding liquids. Okay. Whereas the second statement here, as the temperature around the thermometer bulb heats up, the liquid rises in the glass tube. The glass tube is mounted on the backboard and it's marked with units called degrees. Basically, it's like mounted here. Okay. Then, yeah, before you guys continue copying this, let me just explain this part here as well. This next part here is basically calibrating a thermometer. Now, in order to calibrate a thermometer, it's not like in the factory, as soon as they produce a thermometer, then bam, all the readings are here already. You know, it doesn't work that way. Most of the time, you actually have to calibrate the thermometer. And in order to calibrate the thermometer, you must be given two specific temperatures, which is going to be definite one now, right? Like when this event occurs, right? Definitely this is going to be this temperature, and when this event occurs, it's definitely going to be this temperature, which I have mentioned just now. It is definitely going to be 0 degrees Celsius and also 100 degrees Celsius. Why? Because when ice melts, you can see like the water droplets on the ice melting is definitely going to be 0 degrees Celsius, whereas when water boils, water is like boiling here, this is definitely going to be 100 degrees Celsius. With these two known temperatures here, what's going to happen is we are actually going to start calibrating our thermometer. So let's imagine today, I place this thermometer here into the melting ice now, right? And the thermometer gives me this reading here. Let's say this reading, I know for a fact it's going to be 0 degrees Celsius, all right? I'm not done yet. Then after that, I'll place this exact same thermometer into the hot water here, where the reading gives me something like this. The reading here, maybe it will be 100 degrees Celsius. Now, once I have the 100 and 0 degrees Celsius, the rest of these scales are just a matter of mathematical division only, right? Let's just say, for example, this is a super long thermometer. Let's just say it's 50 dcm. Okay, from 0 to 100 degrees is going to be 50 cm. It means to say each 50 cm, each 50 cm represents 100 degrees Celsius. Each cm must represent 2 degrees Celsius. Right? From here, once I have this information here, what I'm going to do is I'm going to write, okay, after 1 cm, it's going to be 2 degrees Celsius. Another cm, 4 degrees Celsius. Another cm, 6. Another cm, another cm, another cm, blah, 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 all the way until you go to the 100 degrees Celsius. You guys understand what I'm talking about? In terms of calibration, you must have these two known specific temperatures are very, very, very important. Okay, anyone don't know what I'm talking about for this part? Good. 100% absorption rate again. Absolutely what I asked for from a bunch of my classmates, class students. Very good. Yeah, so if you look at this part here, first two fixed points are identified as 0 degrees, which is either the freezing point of pure water, which is usually measured at melting of ice, right? And then the 100 degrees Celsius, which is the boiling point of pure water as well. Having the 0 and 100 degrees Celsius, the rest of the scale is made by dividing the length into 100 equal divisions of degrees here. Like I mentioned, if it's 50 cm representing 100 degrees Celsius, then 1 cm represents 2 degrees. Then you can start drawing your scale on the thermometer. Okay, everyone? Anyone don't know what I'm talking about? Yeah, copy everything down. Okay, everyone, I think you should be done by now. We have 5 minutes left. I'm not going to continue with the rest of this here because it's going to take a lot of time and I'm not going to be able to rush through everything. We will continue this part next week because this part is actually very important. I don't want to rush through it. Instead, what we will do is I'm going to, let me just show you guys what I've been doing over the weekend. I think some of your school already incorporated this already, but basically this is the Google form where you will be doing ABC questions basically. What I have done is I have actually set 5 questions per exercise here. If you look at the number here, right, they are all with reference to my notes. 1.2 is the motion one, 1.3 is the mass weight density, 1.5 forces, 1.6 momentum, 1.7 energy, 1.8 pressure here. I'm done up until here. Basically, each and every one of these numbers here, the third number is representing the set of exercise, set 1, set 2, set 3, set 4, right? They are all still in the 1.2 chapter. What I want you guys to do is, right, especially when you guys are almost near the exam, basically, right, you'll see that this is going to be somewhat of a self-help for you guys, especially when you guys going for exam. If you were to do something like this, right, what's going to happen is you're going to type in your email here. Let's say, and after that, you're going to answer your name here, which is going to be Gabe. Then you're going to start answering all these things using your logical sense of thinking. You know, you're going to type, you're going to press everything now, right? You're going to press. Then after that, you are going to submit to this page. Once you submit, right, you can actually view your score immediately, right? You can view your score immediately. You can see how much you have scored, a total of 3 out of 5 or so on, right? And at the bottom, I want you to actually read the feedback here, guys. The feedback here is going to be, is there basically for you guys for your own self-help, especially when you guys are going for exam. Like for example, today you feel that, oh, I'm not very confident with the motion chapter. You can just quickly do these 20 questions just to give yourself a quick understanding of what's going on. I have purposely spent a lot of time writing down the feedback here, which I think is going to help everyone understand the whole chapter better as well, right? So I just want to know, right, how many of you guys would actually do this if I were to send it to you guys? I'm still in the midst of doing it right now, but I just want to know, right, how many of you guys would be interested in doing this? Of course, if you feel that, you know, I'm probably not going to do this because I'm very lazy, that is your right, of course. You don't necessarily have to do it if you don't want to. But I just want to know, right, how many of you guys would actually want to do these kind of things? I kind of want, so kind of don't want also. The guy. Hmm. Interesting. So 1, 2. Okay. So the rest of you guys, I can only assume you don't want to do it. Yeah, I'll keep that in mind. It'll be free for you guys, by the way. Yeah, I'll just My school been giving Google Forms since first MCU, so I'll pick it. Yeah, actually, I saw from your school, Mishan, like that day when you send me your Google Form, I'm like, oh, it's actually quite interesting. You can do this, and then you can write the predetermined feedbacks and everything. Then it's going to be it's supposed to serve as a self-help lah, especially when you're going for exams. But yeah, I'll keep in mind for those who actually want to do it. Yeah. Once I'm done, then I'll send it to you guys. Okay, that's all I want to know for today. If you have any questions with regards to this chapter here, you can stay back and ask me any questions that you are uncertain of. If you have no questions, you may make a move and enjoy the rest of your Monday night, boys and girls. That is it for today. I will see you all next week. Sir, 2019, the 2.0 isn't the WB, right? What do you mean WB? Oh, it's not in the workbook. Yeah. All right, bye. Okay, welcome. Shen.